Time measures change, but does it cause that change? We use time as a measure of the duration and sequence of events by comparing them with regular physical events. Historically, these included Earth's rotation and orbit around the Sun. For greater precision, we use atomic clocks based on extremely stable atomic frequencies. Through these comparisons, we determine when events begin, how long they last, when they end, and how they are ordered. Because time is present in the measurement of every event, we have confused its role in measuring change with a role in causing change. This confusion appears even in everyday language, as we often describe physical changes as happening over time, almost as if time itself were causing them. If time itself were a cause of physical change, it would have a causal role in the evolution of a system. An object falls because of gravity. Fuel burns through chemical reactions. A train moves because its propulsion system converts energy into motion. We age through biological, chemical, and physical processes within our bodies. Physical interactions and processes produce change. Physical laws describe how it happens, while time measures its duration and order. Time, like a camera that captures successive states of a changing scene, represents change as an ordered sequence of states. The more frames the camera captures within a given interval, the more precisely the progression of change can be resolved in time. But what reveals the direction that change tends to take? Dye spreads without spontaneously reconcentrating. Net heat transfer occurs spontaneously from higher to lower temperature, and spontaneous chemical reactions proceed in particular directions. What connects these processes is entropy. Entropy is an inherent physical property that characterizes physical change and reveals the direction transformations tend to take. Depending on the physical conditions, these transformations may lead toward more strongly bound, concentrated or structured states, or toward greater dispersion. When water freezes into ice, for example, its entropy decreases, while the effects of freezing increase the entropy of the surroundings even more. For spontaneous freezing, the result is greater total entropy. To see how entropy reveals the direction of physical change, consider dye spreading in a liquid. Dispersion has vastly more microscopic arrangements than concentration, so the molecules collectively tend to spread. A similar tendency appears in energy transfer. Microscopic interactions redistribute energy, resulting in net heat transfer from higher to lower temperature toward thermal equilibrium. Yet dispersion is not the only possible manifestation of increasing entropy. When conditions allow unconstrained spreading, systems may evolve toward more dispersed states, as in diffusion. Under physical constraints and interactions, gravity can gather matter, electromagnetic interactions can form bound structures, and barriers can confine matter. Work can compress gases, separate substances, cool regions, and create local organization. In all these cases, entropy still reveals the direction in which physical transformations tend to proceed under specific conditions. But what would it take to reverse a physical process completely? Time does not prevent the return. What makes complete reversal effectively impossible is restoring the enormous number of microscopic components involved to their exact previous states, and the surroundings to their initial state. The arrow of time now becomes clearer. Time describes the order of events, but not the physical direction in which transformations unfold. Entropy reveals that direction. Perhaps the confusion began with a correct observation that led to the wrong conclusion. We saw time present with every event, so we assumed it was the cause of events. Physical interactions produce change. Entropy characterizes how that change tends to unfold and reveals the direction it tends to take, and time measures its duration and describes its sequence.